So, ladies and gentlemen of all ages, there is one variable that plays a critical role in virtually anything we want to study, whether it's physical, chemical, or biological, and it is often taken for granted. We don't consider it, right? It plays a critical role in virtually anything we want to study, but it's often taken for granted. Does anybody want to guess what that variable might be?
Gravity.
Gravity. Gravity is everywhere. It plays a role in virtually anything we want to study. I'll give you two examples. Even a germinating seed knows about gravity. Think about that. A germinating seed knows about gravity because when it germinates, the roots go down, the shoots go up. It's called geotropism. Your body knows about gravity in myriad ways. I'll give you one example. Every time you take a step, your bones are compressed under your own weight. And that sends a bioelectrical feedback back to your body saying, we need bones. Bones are really important. But in a weightless environment in space, there is no bone compression of the astronauts. There is no bioelectrical feedback to the body saying, hey, we need bones. And the way the body interprets that is it's okay to excrete the skeletal system. Seriously, has anybody ever seen the movie WALL-E? It's like it's the basis. It's one of the underlying principles of the movie WALL-E, and so you start excreting your skeletal system, and that's why astronauts have to work with springs and pulleys and tension to force compression of the bones to minimize bone decalcification. So the whole idea of this program in terms of experiment design is, first of all, there is a flavor of essential question that defines all of the microgravity experiments. Let me give you the flavor of question. What is the role of gravity in that, or this, or that thing over there? What is the role of gravity, the variable gravity, in something? If that's the case, if that's the essential question that drives all microgravity experiment design, here's the hard question, here's the important question. What is the variable we have to change? What is the independent variable? We want to understand the role of gravity in something. What needs to be the variable we change?
Gravity.
You got to change gravity and see what happens. If I want to understand the role of gravity in that, I need to change gravity and see what happens. That's how I understand gravity's role. But here's the problem, everybody. I can't change gravity because of this. I can change the temperature, I can change the humidity, I can change the soil composition. I can't change gravity. And let me give you some background in gravity right now. It turns out, we don't know why, but it turns out that any two masses in the universe, like these two coffee cups, are attracting each other with a force of gravity. Any two masses, there's an attraction, a gravitational attraction. But you don't see these two coffee cups flying towards each other because gravity is an incredibly weak force. You need one of these masses to be, at least one of these masses, to be truly massive if you're going to see gravity very easily, okay? So give me an example of two masses where one of the masses is really massive and it gives rise to gravity that you get to see every second of every day of your lives, and you actually depend on it. Give me an example of two masses where one is massive, so we get to see the gravity force, and it is a very personal force for you because you get to experience and depend on it every second of every day of your lives.
Me versus Earth.
You and the Earth, right? You and the Earth. So the Earth is a massive sphere, and you're standing on the Earth. I'll tell you where you're standing. Hang on a second. I'll show you. In the middle of the Pacific Ocean, you're right there. This is you standing on the Earth, right there, okay? But it turns out that the entire mass of planet Earth is pulling down on you. not just the piece of the earth under your feet, but all of the mountain ranges, all of the oceans, all of the continents, the entire crust, the mantle, the outer core, the inner core. The entire mass of planet Earth is pulling down on you with a force of gravity. And that includes the mass 8,000 miles below your feet on the other side of the planet. Sounds pretty impressive. Well, what do we call the force of gravity exerted by all of the mass of Earth on you? What do we call the force of gravity exerted by all of the mass of Earth on you?
Colloquially, we call it gravity.
Well, you call it gravity, but I can tell you that probably any human being older than 4 years old knows exactly what it is.
Weight.
Your weight. Your weight, what you read on that bathroom scale, is the force of gravity exerted by all of the mass of planet Earth on you. It must be a really weak force because it took the mass of the entire planet for you to register 120 pounds on that scale. Does everybody get what I just said? Does that all make sense? Okay. What do you think happens? And you can kind of get this intuitively. What do you think happens to the force of gravity between two masses as you move them farther apart?
It weakens.
It weakens, and that kind of makes sense because the farther away they are from each other, the less they know about each other, right? So the force of gravity gets weaker the farther you move them apart. But here's the question. Can somebody figure out how we do an experiment now based on what we just said, where you're trying to understand the role of gravity in something, so you need to change the gravity variable? So can somebody give me an example of what you might want to do?
Go to the moon.
Go to the moon. So what Justin is saying is go farther from the Earth where gravity is weaker. And I think that might have been what Say was thinking. He was kind of doing something there, but he didn't say anything. He's just smiling. Was that what you were saying too? Move away from the Earth? Okay. So if you move away from the Earth, gravity weakens. So let's see. I it's Ilani, can you think of how to do this experiment? Let's say we move far from the Earth and we conduct the experiment in a lower gravity. Do we need another experiment?
Yeah, I guess if you want to see like the actual effects, you would have to conduct like the same experiment in say like Earth's atmosphere and then do
Very
it.
good. Very good. So the point is that you want to take one experiment and move it to a place where gravity is less, but you have to conduct at the same time the same experiment on the surface of the Earth, so that when you bring the experiment that was in space back, this one operated in lower gravity, this one operated in Earth gravity, and you compare the behavior of what you're studying to understand the role of gravity. What do we call the experiment that we do on the Earth at the same time?
Oh, that's going to be your control.
That's the control. So does everybody understand how this experiment works? Okay, now let's get a little crazy, all right? Let's say I find, what's the tallest mountain on planet Earth?
Mauna Kea.
Well, aha, that's actually a good answer. What is the tallest mountain on Earth above sea level?
Mount Everest.
Mount Everest. It's not tall enough. It's not tall enough. I'm going to find me a mountain 47 times higher than Mount Everest. 47 times higher than Mount Everest. And what's cool about that mountain is when I walk to the top, I am now 250 miles above the surface of the Earth. 250 miles above the surface of the Earth. What's the diameter of the Earth? I said it before. Diameter of the Earth? Anybody remember?
24,000 miles.
Okay, that's the circumference. So we divide by 3.14.
8,000.
So it's 8,000 miles across. So your planet is 8,000 miles across. and I'm on a mountain 47 times higher than Mount Everest. It rises above the surface of the earth to 250 miles. Does anybody want to guess what I can find 250 miles above the surface of the earth when I'm on my mountain? What might I see go right by my face?
Martians and the International Space Station.
Yes, I will discount the first answer and I will go with the second answer, the International Space Station. It orbits the Earth 250 miles above the surface of the Earth. And what's interesting, so everybody with me so far? We good? Okay, so now here's the deal. I have this issue. I'm working on it, but I have this issue. I'm really embarrassed to tell you this, but I carry my trusty bathroom scale wherever I go. So I'm taking my bathroom scale to the top of Jeff's mountain. And here comes the International Space Station. It flew right by my face. I see the astronauts inside. Have you seen videos of astronauts float? Oh, I just gave it away. Have you seen videos of astronauts on YouTube in the International Space Station or on the shuttle?
They appear to be floating.
They appear to be floating. They're floating around as if what does not exist?
Gravity.
It's as if there's no gravity there. There's zero gravity. There doesn't seem to be any gravity whatsoever. And we call that a what kind of environment? It has a special name.
Weightless.
A weightless environment. It doesn't look like there's gravity. There doesn't seem to be any weight up there. And so here I am on the top of my mountain at the same height above the Earth as the International Space Station. I look through the big cupola window on Space Station, and sure enough, the astronauts are floating around as if there's no gravity whatsoever. And I step on my bathroom scale at the same distance from planet Earth as they are, and what do you think I weigh?
Very similar.
You would think very similar, because if I'm at the same distance from the Earth as they are, I must also be weightless. Is that a logical conclusion? Seems like an obviously logical conclusion, because I'm at the same distance from the Earth as they are, so I can't even stand on my bathroom scale. I'm floating around at the top of the mountain. Is there another possible answer that you might come up with?
Wildly different.
In what way? Give me a number. Or give
10
me
times less weight.
I'm sorry?
Some multiplier of times less weight.
And would you say that's a big multiplier, a little multiplier? You could weigh 0. What else could you weigh?
I think I could weigh 25 pounds.
25 pounds. So you're saying that it's pretty low compared to your weight on the surface of the Earth. Say, what do you think?
It's going to be pretty low, because when you're on the International Space Station, it's not that they're only experiencing 90% of the gravity on Earth, but it to do with their microgravity feeling is to do more with the ISS falling around the Earth and there being no floor to stand on. It's why those planes that are going down can also experience microgravity.
So are you saying that me standing on my bathroom scale on top of the mountain, I'm going to still have a low weight? Is that what you're saying?
No, on the mountain, you're going to have a similar weight to what you would on the surface of the Earth.
And Ilani, what do you think?
Yeah, I kind of agree with what Say said about you weighing the same on the Earth if you're on the mountain versus the space station.
Okay, by the way, when I ask all of these questions, is it making you think? When I ask all these questions, instead of just talking, giving you the answers, is it making you think? Do you feel like you're part of telling the story?
I think we're thinking.
Good. Well, it turns out when I step on my bathroom scale, I weigh almost the same as what I weigh on the surface of the Earth in my bathroom. I weigh 90% of what I weigh on the surface of the Earth. So here's my question. What's the diameter of the Earth?
8,000 miles.
8,000 miles. How far above the Earth is the top of my mountain and where the International Space Station orbits? How far above the Earth?
250 miles.
250 miles. So is the International Space Station on the top of my mountain out here?
It's not.
Tell me where to stop. You know how to play this game, right?
There.
Like right there. So what
I
you're
think you were
telling me,
closer for
what you're telling me is that 250 miles relative to an 8,000 mile diameter sphere, wow, the International Space Station is just skimming above the atmosphere. It's just skimming above the atmosphere. Have the astronauts moved very far from the Earth? So what can you say about the force of gravity exerted by Earth on them, their weight?
still remarkably similar to if they were on the Earth.
It's almost the same as what it would be on the surface of the Earth. That's why when I'm standing on my bathroom scale, I weigh almost the same as what I weigh on the surface of the Earth, 90%. But if the astronauts are the same distance from the Earth as me on top of my mountain, isn't the force of gravity exerted by the Earth on them, their weight, almost the same as what they weigh on the surface of the Earth?
But they're falling like in an elevator.
Ah, but that may be the case, but is the force of gravity exerted by Earth on them, their weight, almost the same as
Yes.
it's got to be the same? They are not weightless, they are weighted. They are weighted. They're not weightless. And in fact, the force of gravity exerted by Earth on the International Space Station is causing it to fall around the Earth as opposed to flying off into deep space. So, what's the problem here?
We didn't solve our variable gravity problem we needed.
So, the point is that the astronauts appear to be weightless. They're not weightless, they appear to be weightless. They appear to have no gravity. And the answer is because of what Justin and Say said, which is what?
The falling effect.
They are freely falling around the Earth. And there is a whole section on the website talking about why. You can drill down to that if you want to. But for instance, if you're in an elevator and somebody cuts the cable holding the elevator, and there's no air in the elevator shaft, so there's no air resistance, there's no drag. And as the elevator is accelerating under the action of Earth's gravity, it's falling under its own weight. If there's no friction between the elevator car and the shaft, when you cut the cable, we say that the elevator is in free fall. And if you're in that elevator, you will see in the elevator with no windows that you're floating. You're absolutely floating. There is no up, there's no down, there doesn't seem to be any gravity. As soon as that cable is cut, if there's no air in the shaft and there's no friction along the sidewalls as the elevator car goes down, inside that elevator, it will be as if somebody turned off the gravity switch, just turned it off, and you will be in free fall. The International Space Station is in free fall around the Earth, which means they appear to be weightless. And anything you take to the International Space Station in a freely falling laboratory will behave as if gravity is turned completely off. Let me say it again. If you bring something to a freely falling laboratory, in the case of the International Space Station, it is continuously freely falling around the Earth. If you put something in there, it will behave as if gravity's turned completely off, even though the force of gravity is alive and well and causing it to orbit the Earth. Lei, can you come up with an experiment to test the role of gravity in something?
Did you want that to be for Say or Lonnie or me?
That was for, I'm sorry, for Alani. I'm so sorry. Ilani, can you come up with an experiment?
Wait, sorry, to clarify, the experiment is to test like The
The
effect.
role of gravity in anything you want to study. How would you do that experiment?
I guess, what do you call it? First, you would like define what you want to see a change in. So you could say like, oh, I want to see how like animal behavior changes based on gravity, right? So you would study the animal or study your what do you call it? Your thing on Earth, and then from there you would also study it in a different atmosphere, say on the International Space Station, and then you would compare the two to see if there was genuinely a change in the behavior or something like that.
Okay, so picking up on what Say said earlier, and what Justin said earlier, is one way to do this experiment is move it far from the Earth where gravity is less. And you do the experiment there, and you do the same experiment on Earth in as the control experiment, and then you compare them. But what I showed you is you can't go far enough from Earth to let gravity diminish. It doesn't. The astronauts weigh almost the same as they weigh on the surface of the Earth. So you can't move it away from the Earth and expect gravity to go down much. If you bring it to 250 miles altitude, it doesn't change much at all. But you trick the experiment. You put it in continuous free fall. You bring the experiment to the International Space Station, where it will behave as if gravity is turned completely off. And if you run the same experiment on the ground in Earth, which is what you said, Ailani, what you have is this experiment run with the apparent absence of gravity. This one operated in gravity, and you compare the behaviors of the two side by side to understand the role of gravity. Does everybody see how that works? So now let me demystify it one last piece. Microgravity is weightlessness. A microgravity experiment is an experiment in a weightless environment. That's all it is. And so if you want to, in classic science, if you want to understand the role of some independent variable on what you're studying, that's the one you change, right? Now I'm defining this. I'm defining all essential questions associated with microgravity experiment design. An experiment done in a weightless environment. The essential question all grows from this one flavor of question. What is the role of gravity in this, that, or that thing over there? And to do the experiment, you have to change gravity, but you can't change gravity. So you trick the experiment. You bring it to a weightless environment, in a seemingly weightless environment. You put it in free fall on the International Space Station. You run the control on the ground. And when the flight experiment comes down and you put them side by side, you look for discernible differences in behavior, which will provide you the role of gravity in what you're studying. Does everybody understand what a microgravity experiment is? Okay. Is it pretty? Did I promise that I would demystify it and make it simple?